I guess last Thursday we looked at percent problems. And, I'm following through the book, and it does seem to me that up till now, the book, the direction it goes, seems a little chaotic. We're kind of going from one subject to another. And this subject very definitely fits in there. But I think in the next week or two, things are going to start having more of a, they're going to kind of make sense as they, we're going to go from, one topic that's going to build on another. But be that as it may, we had some kind of problems like, 75% of 200 is what? Well, remembering that 75% really means 75 over 100, and of, in this case, means multiply, and we get an answer. Or you could have something like 450 is what percent of 90? Well, again, there's kind of a, if you do the translation right, 450 is, that's an equal sign. What percent? Well, that's some number x over 100 times 90. All right? And then you just, you work this equation backwards and you find what x is. So that's what we were working on. That's very kind of specific problems that you need to know. We're going to move into an area that's much more general. It's used in a lot of mathematics from here on. And that's going to be graphing. And this is in the book, this is section 4.1. So if you're, if you want to follow along with the book, that's the section we're going to look at. So I'm going to be a little bit specific. I'm sure you've all seen graphs before, but I just want to go over some terminology. Mostly what we're going to be looking at is 2D graphs. You probably have seen a 1D graph, which we call a number line, right? And it'll start at 0. But we're going to look at 2D graphs. And so, that was a terribly unstraight looking line. And at 0, so these lines here are known as the axes. So this is the x-axis. This is the y-axis. And here, where they cross, we have a point which we give the coordinates 0, 0. Each point on this grid will have some coordinates. So, for example, if I have a point here, its x-coordinate is going to be 2, and then its y-coordinate is going to be 3. And of course we move, on the x-coordinate from left to right is positive, right to left is negative, moving up is positive along the x-axis. We have a special name for this point 0, 0. It's called the origin. And for no obvious apparent reason, each quarter of the graph we call them a quadrant. And we label the quadrants or name them. The quadrants start over here. This is the first quadrant. And the coordinates in the first quadrant are either, well, they're positive, positive. In other words, the x is positive, the y is positive. That's not true for any other quadrant. The second quadrant, well, the x's are negative, but the y's are still positive. And we're going kind of counterclockwise here. The third quadrant, of course, everything is negative. And the fourth quadrant, what do we have? The x's are positive, but the y's are negative. I didn't say this, but all coordinates, consist of an x value and a y value, which is just a number on one of these number lines. Well, again, just for historical purposes, these are called Cartesian coordinates. They're named after René Descartes, a Frenchman, philosopher, mathematician. He's famous for coming up with the statement, "I think, therefore I am." And since this is not a philosophy class, I will not attempt to explain what that means. Although, 200-300 years ago, it was very common for, mathematicians and scientists and philosophers to kind of overlap. There wasn't perfectly clear who was what. Okay, so this is your basic graphs. We're going to do some more with it. I just want to ask: are there any questions about the graph right now? I guess we should just go over kind of one or two kind of examples that we might do with this. If I asked you to graph a point, let's say -3, 4, right? So a good place to start is the origin. We look at the x-coordinate, that's -3, so we're going to go over 1, 2, 3. And from here we're going to go 4, 1, 2, 3, 4. And that's our point. All right, that should be straightforward. If I asked which quadrant it's in, you can just look at the graph and see immediately it's in the second quadrant. But without even doing this, you could just look and see, because the x is negative, the y is positive, that's always the second quadrant. Anything else that's, like on an axis, you could just say on the x-axis. It's not really in a quadrant. On the other hand, if I just picked a point, I'll try, I don't know, pick a point out here, and I said, well, what are its coordinates? Well, you could go, well, wait a minute, 1, 2, 3, that's -3, then 1, 2, -2. Obviously, going to be a little more accurate on graph paper, or so. Those are the basic things we're going to deal with. We're going to advance on that a bit. But before I do that, though, I want to talk about again topic we talked a little bit before about, but more specific. Problem solving. And I'll add approaches, different ways to approach problem solving. So one of the ways we can do this is what I'm going to call the numerical approach. There's a whole bunch of methods involved here. We used one called guess and check, where you just guess a number, you check, you see, is that close to the answer? If it's the answer, you're done. If it's not, you try something else, and you see what was the result of your second guess relative to the first, and you try and hone in on the solution. The thing about if you just do a pure guess and check, you may not get an exact answer, and often we use numerical approaches because that's all we want. In science or, say, engineering or architecture, we're not always looking for the precise mathematical solution to something. We just need something within the accuracy of our constraints. We're building a building. We don't need the building more accurately, defined. You could define it, say, 1/100th of a millimeter. Well, it's not necessary, right? Whereas in math, often we're actually interested in the exact answer. But numerical approaches is part of math, and it gives you a solution. The second strategy is an algebraic approach. Well, you're all sort of familiar with this idea. If I put up an equation like 2x plus 3 equals 5, and I want to know what x is, right? Well, you could guess and check this, and you'd probably get the exact answer pretty easily. But algebraically, we have some rules that we can follow. We can subtract 3 from both sides. So we'll get 2x plus 3 minus 3 is just 2x. And 5 minus 3 is 2. And then we can divide both sides by 2. So we'll get x equal 1. And we get algebraically an exact answer. Now, we're going to look at problems more complicated than this. But I just want to point this out. This is a different approach from, numerically just kind of trying to find your way to the answer. And then finally, we have here a graphical approach. That is to say, we use the maxim that a picture is worth 1,000 words. We draw something, we draw a graph, and we see what we can learn from that graph. An example might be kind of pulling this one out of my hat, so let's see if it works out okay. If I had two equations, I had, say, y equals 3x plus 2. Well, we're going to look at how we would graph that, but for now I'm just going to pick some numbers. I'm going to say, well, if x is 0, well then y is 2, right? If x is 1, y is 5, and I'm going to plot those numbers. 0, 2, and then 1, 1, 2, 3, 4, 5. And since this is what we call a linear equation, I know the graph's going to be a line. You can kind of draw a line through it. And then if I had another equation, like x equals minus x plus 2, Well, again, I could pick some numbers. Oh, I made it too easy, didn't I? There we go. And I'll plug in 1. Negative 1 plus 4 is 3. So, okay, 0, 4. And 1, 3. Okay, so now I have a line here. And I'm looking for a solution that fits both of these. And now I can kind of see that, oh, it's, you know, if I drew this nice and clearly with graph paper, I might guess it seems to be about 1/2 and then about 3.5. The nice thing about the graph is you can kind of look at what's happening here. If these equations had some particular meaning, like I'm trying to sell some product at a certain price, you know, and I graph that, and I'm hoping, you know, the public is going to buy it at a certain, you know, they're going to buy more of them at a certain price than another. I can kind of see graphically, you know, what this means, that this point is where these two curves, where they intersect. So that's another way. Okay, I guess we're gonna demonstrate a little some of these approaches a little here. All right, so I want to look at a particular problem. We have an equation, 6x minus 2y equals 4. And before I try and solve it, I want to put it in what we would call functional form. We're going to talk about functions on Thursday, but for right now, just know that I'm going to solve for the y value. I want to have the y value over here by itself. So the first thing I'm going to do is I'm going to subtract 6x from both sides. And then I'm going to divide both sides by -2. So on this side, I just end up with y equals. If I divide 4 by -2, I'm going to get -2. And if I divide -6x by -2, I'm just going to get 3x. So now I have the equation in its functional form. And this will make it right now easy to create a little table of the values. Again, this is more of a numerical approach. So I'm going to start at -2. If I plug in -2, I get -6, -2, I have -8. -1, well, -3, -2 is -5. 0 is always a nice value to try and plug in, because we can just skip this part, right? It's just -2. And then a couple more values. 1 will be 1, and 2 will be 4. All right. Well, we can take a look at this and just learn a little bit. From zero down, all these are negative, and then from above 0, 1, they're all positive. I haven't really been specific what this problem is about, but at this point you can kind of get a feel for what the results look like. If this describes some real-world situation where these output values only have meaning in a positive way, like if I said, if you dig so many hours, you'll find so many gold nuggets. Well, it doesn't make any sense to get negative gold nuggets. You can't do negative work. So you could just immediately say, these values don't mean anything. But again, you can take a look at this and get some kind of feel for it. All right. Now, let's stick with this equation for a second here. If I kind of randomly picked some value and said, I wonder if this well, when I say value, I mean an x and a y value. If I said, well, does this pair, is this a solution to this? From a graphical approach, that would mean, is this point on that line that we graphed? Well, how do I go about this? Well, I just have to plug in, right? There's my 20 is my y value. 7 is my x value. So 3 times 7 is 21 minus 2, which is 19. So I immediately see it's not a solution. I might note, sometimes we're going to solve some problem. We're going to get an answer. And it's always good to check your work. Sometimes it's easier to just plug in after you've solved something to see if it fits. That's a good way to check your work. All right. I apologize. My glasses keep steaming up. Does anyone else have that problem with masks? Yeah. I do have a solution. Just takes a couple seconds to dry. Okay. Okay. I want to go back to graphing here. In particular, I want to talk about graphing an equation like this one. Okay, we're going to use 3x plus 5 equals 3x plus y equals 5. And again, I'm going to put it into the functional form, so it's y equals minus 3x plus 5. Now, if you remember from geometry, does anyone remember from geometry how many points you need to determine a line? Okay, all right. We've got answers. The answers are kind of like, I have the answer, I have the answer. I have the answer, yes, that's right. Thank you. 2. You need just 2 points. So if I were to draw a graph, and I want to plot the line that this represents, I just need 2 points. There's no reason you have to pick a difficult point. So a good point to always use is x equals 0, which in this case is 5. And then you can pick another point that you like. 1 seems pretty easy, right? So that's 1 and 2. So we just draw these points, 0, 1, 2, 3, 4, 5, and 1, 2. And imagine, if you will, I have a ruler here. I can draw a nice straight line. And this line represents all these solutions to this equation. Now, I imagine a lot of you have seen this before, but I'm just going to point this out. We have the equation in this form, and the line goes through the y-axis at 5. This is not a coincidence. We call this point the y-intercept. And when the equation's in this form, this number here is the y-intercept. Now, there's also, this line also passes through the x-axis, right? And we call this point an intercept too. It's the x-axis, the x-intercept. And how would we find this? Well, we know this is the point where what? Where y is 0. So if we write this as 0 equals minus 3x plus 5, and we solve this, right? We add 3x to both sides, and then we divide by 3. We can see that this point is going to be at 0, 5/3. So when you're graphing a line, it's often a good idea to just find the 2 intercepts. And then you plot those and you can draw your line. We're going to learn some other strategies too to graph a line, but for now this works pretty well. Not all equations look exactly like this. There's another kind of equation we're going to look at. I think I got to take this over. In this example, we're going to use an absolute value. And we want to graph this function, this equation. With an equation with an absolute value, the thing to note is that there's a particular x where something funny happens, right? Right? When what's in here is below 0, it gets switched to positive, and when it's above 0, it just gets left alone. And the place where that happens is at 1. So we can expect something special to happen at x1. Well, at 1, the value is 1, 0, right? We plug in 1, the y is going to be 0. So something interesting is going to happen here. Since it's an absolute value, it's not going to go below, right? We can kind of, right? It's never going to go negative. And this looks a lot like the equation over there in a way, in that there's just an x, not an x squared or a square root of x or anything. It's going to be a straight line. From the right on, it's going to be a straight line, and from the left on, it's going to be a straight line, just not the same straight line. So let's just try a couple values here. So we already found that 1 is 0, 2 will be 1, 3 will be 2. So we can see what's happening here. But if I go in the other direction, if I say, well, how about 0? Well, 0 minus 1 is negative 1, but the absolute value is 1. Okay. 1 minus 1. Minus 1 minus 1 is minus 2. But that just becomes 2. Minus 2 is going to be minus 2 is going to become 3. So this is going to go this way. So this is y equals absolute value of x minus 1. This is very typical of an absolute value graph, where on one side of this point, it'll do one thing, and on the other, something else. All right. All right, I want to kind of push my luck here. I want to see if I can get this technology up and running quickly. Who here, by a show of hands, has worked with Desmos? Oh, yay! Okay, so I don't have to say that much. Please ensure Mac Mini is on. Okay. Every time I've tried this before, somebody left the computer on, so take another minute here. Desmos is just, it's not the only tool like this, but it has the nice feature it's on the internet, and it's very easy to access. So if you haven't seen it before, over here on the left you can type in an equation. It's actually one of the friendliest, algebraic inputs I've ever seen. If I say x and I say hat, it knows it's a square. And then I can just add something else. Okay, so here we have something you can use at home when you're doing homework is kind of a check. Or if I ask for a graph, you can just do the graph off of here. this particular equation, we're not going to get to quadratics. This is a quadratic, meaning it has a square in it. That sounds a little, does that sound kind of odd? Quadratic 2. Quadratic should mean 4, right? Yeah. The reason for that funny numbering is, I'm not sure if it goes back to the Greeks, but when they would try and solve an equation with an x squared, they would actually use a square, which is, I think, where it became quadratic. Well, anyway, if you're on a desert island and you don't have Desmos around, you can still kind of build a table. And what have we got here? Negative 4 plus 4, well, that's 0. Negative 1 is 3. 0 would be 4. 1 would be 3. And 2 would be 0. Okay. So, assuming I'm not going to write on the screen here, but sure enough, you can look at these points. Negative 2 is 0. Negative 1 is, okay, that's up here, 3. 0 is 4, so forth. So, this is another way to produce a graph or check your graph. All right. I'm going to put this away now. All right. I did this once already, but I'm going to go over it again as a way to graph a line. We're going to take a simple equation and y equals negative 2x plus 4. And we're just going to try and graph it by finding the intercepts. The intercepts being, the points where it crosses these axes in which one of the coordinates is 0. So for one of these, the x will be 0. And for one of them, the y will be 0. So let's take the x first. Well, if the x is 0, we can see immediately the intercept is 4, the y-intercept. If we set y equals 0, well, then we have to do a little work to solve this. We can add 2x to both sides and divide by 2, and we get x equals 2. So again, as a simple way to graph a line, we can just plot these 2 points. 0, 1, 2, 3, 4, that's the y-axis, the y-intercept. and 1, 2, 0, that's the x-intercept. And again, just draw a line through those 2 points. All right. I think this is the only skill you have to take away from this class today. But I have some other kind of interesting things to say about graphing. It's possible to draw a representation, a graph of something that is not just limited to 2 dimensions. You can add a z-axis, which, although I've just written it as a diagonal line, you think of it as just coming right out of the board visually. And if we pick some point, like, I don't know, 2, 1, 3, well, normally we would go 2, 1. And how are you going to represent that z-axis? Well, it doesn't hurt. I guess it would be better if I had a different color. Do I have a different color here? I left my colored pens somewhere else, so not today. You kind of draw this three. I'm not the most artistic on the blackboard, but you can see this point here kind of sticks out, and you can represent it. You could even draw 2 points on here and draw a line between them, representing a line in 3D. Yes, I should. 3D, right? So that's something else you can do. You can go a step further, but it gets a little hard to imagine. We do this in mathematics. Sometimes we want to think about a 4D object. Well, let's start with a 3D object. I'm going to draw a cube. And maybe I should, since some of these lines are hidden, I should kind of draw them that way. Well, what would a cube look like in 4 dimensions? Well, think about how we got from a square to a cube. Well, we drew another square and we connected the vertices. So I could draw another cube. And then I could just, in the 4th dimension, if you can imagine that, I can attach the vertices. Since I've got 8 vertices, there'll be 12 of these connecting pieces. I'm sorry, 8. There'll be 8 connecting pieces. I'm sure there are better looking examples. This is not the only way you can represent this. Really? I guess that's it. Before you go, does anyone know what what the four-dimensional cube is called? You can Google this. I'm sure, especially if you Google it at IMDb, this is called a tesseract. I better get tesseract. Yeah, it'll show up in sci-fi where people are caught in a tesseract. They're moving around in 4 dimensions. All right, there's a assignment posted, but it's kind of for today and Tuesday if you want to look at it and get started, but don't, when you run into the section on functions, keep in mind we haven't gotten there yet. So, okay. Any questions? Okay, everybody's good. All right, thank you.